Thank you. Yeah, so it's really nice to be here. I've been enjoying the long program, and also been enjoying the workshop this week. So thank you to the organizers of both programs, and thank you to IPAM for hosting such an awesome experience. So today I'm going to talk about this is a relatively recent work on Subspace Langevin Monte Carlo. And the basic questions I want to ask are, how do we start to think about simplifying optimization in Wasserstein space? And what sorts of things should we pay attention to when we do this simplification? Like what sorts of constants should our guarantees depend on? So the motivation that we'll kind of get back to at the end is the sampling problem. So this is one of your typical optimization problems in Wasserstein space. It has applications in machine learning, statistics, optimization, and so on. But one of the key problems is that when you're sampling in high dimensions, it's typically a challenging problem, right? Distributions can be very ill-conditioned. They can have all sorts of crazy shapes, right? Like in diffusion models. What does the distribution of natural images even look like? In terms of implementing high-dimensional sampling algorithms, Langevin algorithms typically work decently well because they only rely on first-order information. Right? You would take a gradient step, as we'll see. But as you, again, start to scale things up, you may want to add sorts of adaptation, like you do for gradient descent. But you quickly run into problems with memory and complexity constraints. And so the perspective that I want to emphasize here is you can really think about sampling as an optimization problem. So maybe we can draw ideas from how we do efficient optimization over Euclidean spaces to make sampling algorithms more efficient by thinking about sampling as optimization. OK, so I'm going to start really basic today, and I just want to review some of the kind of quintessential results for how we think about the convergence of gradient and coordinate descent, as well as subspace descent in Euclidean space. Talk about how we might extend this to Wasserstein space, although this extension is still kind of work under construction. But at the end, I'll give a more concrete example of how we actually use these ideas in subspace in the Langevin algorithm to develop more efficient algorithms for this that are actually adaptive as well. OK, so let's talk about Euclidean optimization. So our basic workhorse algorithm these days for optimization problems over RD, they want to minimize a function f, is to perform some sort of gradient descent. So at each iteration, what I do is I look in the direction of the minus gradient, and I take a small step in that direction. And my step is scaled by this factor hk. OK, and I think I've lost my little mouse. That's OK. So hk measures how far I'd like to step along this minus gradient direction. And if your function is well behaved, this should decrease your objective value. And a fixed point of this algorithm would be a stationary point. One way of thinking about this is as a discretization of a gradient flow. Right? So gradient flow would be at each point in time, a particle wants to move in the direction that points most downhill. And so if you could run things in continuous time, you might implement this flow. But unfortunately for algorithms, we need to discretize. And so this would be your forward Euler discretization of this gradient flow. How do we analyze the convergence of gradient descent? We come up with all sorts of assumptions on the function f to do this. The simplest argument for convergence of gradient descent relies on things like convexity and smoothness of your function. So we're going to say a function is strongly convex if it satisfies this quadratic lower bound at every point in space. And the function will be beta smooth if its gradient is Lipschitz. Okay, you can have another definition of smoothness here that we'll see later on that corresponds to having a quadratic upper bound. But to talk about gradient descent in comparison to coordinate descent, it's a little bit more convenient to work with this definition of smoothness. OK, so under these two assumptions, we have our typical theorem of convergence that says if I take my step size to be 1 over the smoothness, then I achieve epsilon error as soon as my number of iterations is like kappa times log 1 over epsilon. Okay, kappa here is my condition number. It's this beta over alpha that kind of measures sort of how well conditioned the problem is. And the dependence on epsilon tells you that you have a linear convergence rate. Okay, so just want to mention there are many equivalent conditions you could use to these two conditions and still achieve linear rates. You can even move beyond convexity and talk about things like Polyak-Wolyashevich inequalities and still get the same linear rate. So this is what we see with gradient descent. Okay, you don't just have to do gradient descent, though. Maybe you don't want to compute your full gradient at every iteration. And maybe instead, it's much cheaper, in fact, to just compute one partial derivative at each iteration and then move along the coordinate corresponding to that partial derivative. Right, so here my grad I will just be a vector that zeros everywhere except for the ith coordinate, where I put in the ith partial derivative of my function. So what random coordinate descent does is says, let me pick one of my coordinates uniformly at random at each iteration, and then take a step in the minus partial derivative direction, okay, along that coordinate. Okay, so you end up with these steps that are a bit more zigzaggy rather than this sort of nice path that takes you to the minimizer of your function. So when we talked about the convergence of gradient descent, we had this condition that's beta smoothness, right? So the function is smooth if its gradient is Lipschitz. What do we do for coordinate descent? What parameter does coordinate descent rely on? An analogous analysis of coordinate descent relies on coordinate-wise smoothness. Okay, so this is adapted to the choice of updates that you're making for coordinate descent. So we say that this function is beta I smooth along coordinate I if this inequality holds. And the way you can kind of read this is that the ith partial derivative is Lipschitz with respect to the ith coordinate. Okay, is this condition clear? Right, so again, this is a one-dimensional condition now, right? I can only move along the ith coordinate in the ith partial derivative. Okay, now how does this compare to your notion of smoothness? Well, you can pretty easily show that this beta I is upper bounded by the beta from this original smoothness if f is beta smooth for all I. And typically you would expect there to be some gaps, right? So here's an example function where it's a short computation to see that the top eigenvalue of this matrix is 3, right, which would correspond to this Lipschitz parameter beta. But beta I is 2, right? So you think beta I is typically smaller than beta in generic examples, and especially in cases that are ill-conditioned but have been rotated appropriately. Okay, and the key point is that now, when I do the analysis of random coordinate descent, I have to do a couple things. So first of all, now I measure error in terms of this expected difference because I'm doing random coordinate descent. But that's OK, it's random. But now what do I pay? Well, instead of paying beta over alpha, which was my condition number, I pay in terms of the maximum directional smoothness parameter over alpha times a factor of d. OK, so this factor of d we can kind of ignore because each iteration requires only one partial derivative. So if we measure our complexity in terms of number of directional derivative calculations, then the complexities match up with respect to this d parameter. But we actually are saving now on the conditioning, right? The conditioning is now measured with respect to this better smoothness parameter beta I. OK, so we see that maybe in general it's better to try to use coordinate descent algorithms because they're better able to adapt to smoothness of your function. Now, coordinate descent isn't always great, right? For certain non-smooth functions, it can get stuck, right? The typical example is a sort of a diamond function with diamond-shaped contours, where no matter which coordinate direction you look in, you're always going uphill. And maybe another deficiency of this is that, in its stated form now, right, beta I only depends on coordinate directions. So maybe some rotation has been applied to your function to make, beta I as bad as possible, right? Maybe beta I is just as bad as beta. Okay, so to generalize this, to sort of get around this issue, you can go from coordinate descent to block coordinate descent, right? So not only do I update along one coordinate, but maybe I choose r coordinates at each iteration, and I do my update along that block of coordinates. And furthermore, I allow those coordinates to point in arbitrary directions, right? So now this corresponds to taking directional derivatives along the columns of this orthogonal matrix U. U. Okay? So at each iteration, now what do I need to compute? Well, I need to compute r directional derivatives instead of one directional derivative. Fortunately, it doesn't get stuck as easily, but you can still construct examples, of course, where this gets stuck, but full gradient descent or subgradient descent might not. And the complexity scales, like we might imagine, in terms of this max directional derivative parameter, where now this directional smoothness again corresponds to the notion of smoothness you might expect as the generalization of that directional smoothness to r dimensions. Notice also that now I have d over r rather than just d, because I'm sampling r coordinate directions at each iteration. So that at least interpolates when r is 1, I get the coordinate descent result, and when r is d, the d's cancel. Okay. Now, maybe as a generalization of all of these ideas, I don't need to fix my basis in advance, and I could just think about choosing a random subspace to project my gradient to at each iteration. And this is the idea of subspace descent. So at each iteration, what I might do is pick some projection matrix P, pk, that's formed from some orthogonal, semi-orthogonal matrix uk, and just take a step along that direction. So you can think my blocks are changing at each iteration, as well as the randomization I do. What you can show is that, again, you get a similar result to what we just had. The only thing that now changes is that I have a maximum over beta, where worst case beta is, this beta measures the possible betas I could see from the directions that I sample. So again, you get maybe some better adaptation with respect to beta, which is nice, because you're only going along r directions instead of d. You maybe get away with reduced memory and computation, and this plays nice with zero-order ideas. But this doesn't look so much different than the guarantee for block coordinate descent, right? This kind of looks the same. And this is even worse if the coordinate directions live in this sampling distribution that you choose. Now, maybe an intriguing experiment is that it's actually typically better to do uniformly random subspaces than trying to choose the blocks in advance. So this is some quadratic function in dimension 100 that you only see the contributions of the first 20 variables. And here I'm setting r equals 2. This is the sort of block updates I'm allowed to do as rank 2. And we see that when we compare the convergence of coordinate descent and subspace descent to gradient descent, the subspace descent does much better. Right here, coordinate descent is block coordinate descent with 2 choices of coordinates. So unless you know good blocks in advance, it might actually typically be better to just use uniformly random subspaces, because it ends up being better adapted. Okay, and there's more examples in this paper by Kozak et al., where again you see this uniformly random subspaces tend to perform better for gradient descent than just coordinate descent or block coordinate descent. Okay, but this I think is still not well understood. How do you select good subspaces at random to do this subspace descent in general? OK, so this is well and good. This is kind of the state of the literature for gradient descent, going to coordinate descent, going to subspace descent. But we don't have any of these simplifications yet in Wasserstein space. Right? When I do optimization in Wasserstein space, we talk a lot about gradient flows. But how can I start to think about methods that are maybe better adapted to things like directional smoothness in Wasserstein space? Right? We don't yet know how to do these things. But I want to sort of start to hint at, in a specific example, we can start to see these things show up. And that's in the case of the Langevin algorithm later on. OK, so I'm just going to skip this slide. We've heard enough about Wasserstein space. But suffice it to say, I'm working over 2 Wasserstein space here. And hopefully, everyone has seen the geometric structure of Wasserstein space. I can compute geodesics. It's a geodesic metric space. I can talk about what happens when a measure evolves according to some time-dependent vector fields. It has a nice differential structure with an accompanying Riemannian metric. And I can define things like gradient flows. Right? So for a function f that maps measures to real numbers, I can compute the 2 Wasserstein gradient, which is the Euclidean gradient of the first variation. And I can define a gradient flow as solving this continuity equation. OK, and maybe try to implement this to do optimization of my function f. OK, so in practice, right, you can't just say, give me a PDE and say that this solves your optimization problem. Right? You need to actually try to implement it. So you could try to say, OK, let me do the analog of Euclidean gradient descent in Wasserstein space. So given my function f that now maps measures to real numbers, I want to minimize it over probability measures. And so what I might do is repeat this iteration, where at each iteration, I take a step in the minus gradient direction. Right? So what this implements here is essentially just a geodesic step in the minus gradient direction, assuming all the measures here are absolutely continuous. OK, so you can do this. And people have done this in cases like Berry center functionals. And you can think about this as a discretization of a gradient flow. Right? This is really just a forward Euler discretization of this sort of PDE here. Now, there are lots of issues that immediately come up when you try to do something like this. Right? How do you choose HK? Right? In order for this to be a well-defined step on Wasserstein space, this HK needs to be small enough so that you stay on a geodesic. So this is really tied to properties of your measures as well as properties of the function f. So directly implementing this gradient descent procedure is hard in general. Now, you could just naively, ignoring all of these things, try to write down an analysis of this gradient descent in Wasserstein space and just write down what the analogs of smoothness and strong convexity are for Wasserstein space. And these are what you might choose. As I mentioned, a substitute for that Lipschitz gradient condition is this quadratic upper bound. And so this is the analog of the quadratic upper bound in Wasserstein space. And if you go through the analysis is exactly the same. And you get this linear convergence result for a certain choice of step size. Now, again, this ignores lots of things, right? Like general functions that we like to optimize in Wasserstein space, like the one corresponding to sampling, doesn't satisfy this. And furthermore, right, when I say you can do this, right, I'm implicitly telling you that you're able to exactly compute the gradient, which we can't necessarily do in general. And you have a good representation from UK, which again is maybe problem dependent, or I only have a representation for in parametric cases. But in general, this sort of procedure doesn't need to be parametric. OK, so this result is a bit vacuous as it stands. But we can still try to analyze this even more. So I'm going to skip the continuous time stuff and just move straight to subspace descent. we can try to play on this procedure and just say, OK, what happens if I try to restrict update directions to subspaces? So my directions now are going to be just projected Wasserstein gradients. So I'm going to define an update where I push my measure along some low-rank projection applied to this Wasserstein gradient. Again, you can at least see here that fixed points of this need to be stationary. And now I have simplified things a little bit. I haven't simplified the first variation here, but I've at least said that now I only need to compute, say, R directional derivatives of this first variation in order to implement this procedure.
Sorry.
Yeah.
Here the low rank, it's low rank in the space of the particles or in the space of the distributions?
So this is basically saying that when I apply this to this gradient, what I end up getting is a low-rank vector field. So the vector field at all spaces lives on a low-dimensional subspace.
But
so
it
what you
doesn't
see in this,
necessarily live in a low-rank space.
huh?
It doesn't live in a low-rank space, it's low-rank.
The vector field lives in a low-rank space, but not the measure. So yeah, so what happens here, right, is I have this measure mu naught, and what you see is the Wasserstein gradient might point in all these different directions, these blue directions. But if I choose a v that corresponds to maybe this u, right, maybe I should have written u there. If I project all the vector fields onto that, all the vectors point in one direction. And so the measure would just travel along that. Of course, the vectors are scaled.
Yeah.
This will also modify the tangent cone, right?
Yeah, of course. Yeah. So, for example, now, what is an issue with this? Well, you're no longer stepping along geodesics, right? Like this is not, when you expand this out, you're no longer moving along gradients of functions, which is what you need to be able to do to say you're moving in Wasserstein space. But regardless, you can still apply this, right? This is just some transport map. And OK, so there's maybe some way of analyzing this in continuous time. Again, for sake of time, I don't want to talk about this. The one thing I want to mention here is that when I'm doing this, I'm, of course, projecting my vector field, right, to some low-dimensional subspace. So I am simplifying my vector field. But this isn't necessarily like an intrinsic, I'd say, subspace or coordinate descent in Wasserstein space. Because, right, I'm only really projecting this gradient here, but really I see there's this other derivative here, right, this sort of infinite dimensional derivative. That's the first variation of f. So something I am interested in thinking about more in the future is, are there really better intrinsic ways of doing coordinate descent in Wasserstein space that don't necessarily rely on just projecting the vector field? OK, but leaving that for future work. What I instead want to do is shift gears a little bit and talk about how this subspace procedure, what it actually looks like for a specific gradient flow. And that's a gradient flow corresponding to this KL divergence. OK, so as I mentioned, Langevin algorithms are nice in that they allow us to sample from high-dimensional distributions. Because if I have access to this potential v, I could compute its gradients and run something like a noisy gradient flow. And we have this nice correspondence between the Langevin diffusion and the Wasserstein gradient flow. Right, from the measure point of view, I could define the gradient flow of this function by computing its Wasserstein gradient and defining this gradient flow. And I get an equation that describes the evolutions of measures in space and time. Now, on the other hand, I can define the Langevin diffusion as the solution to this SDE. And my particle then moves through space and time. And I arrive at different x's at different points of space and time. And the key thing to know here is that if my x naught is distributed according to mu naught, then I have this correspondence between the mu's that solve this equation and the xt's that solve this SDE. Right, so the SDE you can think about as a particle level implementation of this gradient flow. Now, one reason this is nice, right, is like if we try to discretize, discretizing the SDE is much easier than discretizing that gradient flow. As I mentioned, and as we'll see in a second, to discretize this gradient flow, what I would need to do is characterize how well behaved is this function, f. And this function f is not at all smooth, right? So even trying to implement gradient descent here is a little bit hard, although people try to do this in places like normalizing flows. But discretization on the particle level is pretty easy in quotes. You could maybe just do the forward discretization by say, OK, what I'm going to do is I'm going to first take a step according to the potential, which is this minus grad v, and then add noise after the fact. So this is your forward discretization. That's what I do is I take a minus gradient step, I scale it, and then I run my Brownian motion for some amount of time. This ends up yielding biased samples, but they can be corrected, of course, by doing various things like taking your step size to 0 or doing a Metropolis-Hastings adjustment. But notice that, again, you need to be able to compute the full gradient, and this can actually perform poorly on highly ill-conditioned problems. And to give you a sense of why that might be, if the main thing to read is here, if my potential V is strongly convex and smooth, then this KL divergence term here is strongly convex and smooth, the first term, this V term. And the second term, H, the entropy term, is convex. So I might have hope for some rates in this problem. And you could essentially use these ideas to show a rate of convergence of this Langevin Monte Carlo, this discretization of the Langevin diffusion, that has an iteration complexity that looks like this. So you see familiar things. You see kappa log 1 over epsilon. But there's, of course, an epsilon squared here. This is due to the fact that this entropy term is non-smooth. So we can't just get the linear rate of convergence. But we're also doing a forward discretization. And that's what's being analyzed here. But this is sort of the best dependence that we know for this forward discretization of the Langevin diffusion. Right? So the dependence we should expect is kappa d over alpha epsilon squared times this log term. Now, this argument that was conducted in this paper heavily relies on convex optimization and is better than the previous arguments that relied on coupling, where what you end up seeing is you need to take a smaller step size by a factor of kappa, and you end up getting a kappa squared in the iteration complexity. So the iteration complexity actually grows by a factor of kappa if you're not careful in the analysis here. Okay, this will come back into play when we talk about the subspace variance of this algorithm. Okay, so in 2021, there were a couple papers by Ding and collaborators about random coordinate Langevin Monte Carlo. The basic idea is, OK, instead of doing this full Langevin step at each iteration, maybe I could just do the Langevin step along one coordinate and then repeat this. And let's kind of see what happens here. Notice that now I'm projecting both this gradient and the noise term. So really, this is kind of a forward discretization of a subspace of that subspace descent in Wasserstein space because my updates can only occur along this one-dimensional subspace. In terms of computation, I do save per iteration. I only have to compute one partial derivative. And the noise is also only added in one dimension. So that's important. Now, when we analyze this, what do we expect to happen? Well, when we go back here, this kappa, again, is the condition number corresponding to the Hessian of V, right? So it's, again, beta over alpha. So what I might like to show up now that I'm computing only directional derivatives of v is I probably should have those directional smoothness parameters show up. And this is exactly what they prove in their paper. Right? So if my function v is strongly convex and satisfies those directional smoothness conditions that I mentioned earlier, then I get an iteration complexity that looks like this. So now I depend on kappa I rather than kappa. Now the issue that you see here, right, is okay. First of all, I have a factor of d that shows up, and that's the same here. But the kappa is now squared rather than it not being squared. And this is due to the fact that to do this argument, you end up having to do a coupling argument that's similar to that suboptimal coupling argument that I mentioned earlier, right? The one where kappa squared shows up. That being said, you can actually improve this result, and they do in the paper, to say if I sample coordinates proportional to the directional Lipschitz constants, then this iteration complexity improves to the sum squared rather than d times the sum of the squares. Okay, so in this paper, right, okay, you can now say that if my function is really ill-conditioned and the sum of the kappa's quantity squared is less than kappa d squared, then this random coordinate Langevin Monte Carlo should perform better in terms of cost measured in number of directional derivatives computed. Right, that's why there's this extra factor of d for Langevin Monte Carlo. Okay, so this was the best that has been done previously for these arguments. Now, I don't necessarily believe that this should be a kappa squared, and I think that there might be a way around this, but again, we'll see in our results that we still have this squared dependence, even though we're going to have better dependence on the conditioning because of directional smoothness rather than global smoothness. Okay, so one direct extension of this that requires almost no work is the block coordinate version of this. So you could rotate your axes, and you can compute derivatives with respect to blocks of coordinates, and of course get the analogous result, again with a kappa squared, same coupling argument and everything. Again, it's best to take your sampling probabilities of these blocks to be proportional to the directional smoothness, in which case you end up with a sum of kappa squared rather than the d times the sum of the kappas squared. Okay, but now you get dependence on these directional smoothness. Okay, but this isn't where we stop, right? You can do much better than this. Right, as I mentioned, maybe back at the beginning, right, the sampling distribution of your directions really influences the convergence of this method. So as an example, right, this is that same function again, but now in the Langevin setting. So now I want to sample from that low rank distribution. And if I do block coordinate Langevin, that's what this coordinate thing is, I get some error. But I actually get much better error if I use just uniformly random subspaces. So the sampling distribution of my updates really matters. And I can do even more adaptation by appealing to preconditioned Langevin algorithms. Okay, so I'll quickly just say what these are. So what you can do to the Langevin diffusion is you can add these extra matrices and not change the stationary distribution. Okay, so what preconditioners am I allowed to add? Well, I can add PSD matrices that multiply the Brownian motion and the potential. Can also multiply the potential by a skew symmetric matrix. However, when I multiply my drift or my potential by these things, I need to add a correction term. This is sort of my Riemannian correction for having done these preconditionings. Now, in practice, right, it's expensive to compute this thing here. Derivatives of matrices, you don't want to have to do that in practice. So what you might do is, throw away this gamma term. And, there are cases where Q can help a lot, but let's just ignore Q for now and just focus on the discretized version of the preconditioned thing where I now only have my A. Despite the fact that it yields biased samples when HK goes to 0, the bias doesn't tend to be too bad in practice. Okay, and you can also use this as a proposal for a Metropolis-Hastings algorithm. That's fine. Or what you can do is just make A independent of X. Right, so A here. The reason that this correction shows up is that it has a derivative. So if it doesn't depend on X, then that goes away. Right, one way to make this adaptive, right, that, again, we're exploring in ongoing work, is instead of making A depend on X, make A depend on the distribution of X. Right, that way it still adapts to the sequence of measures mu k, but it's constant with respect to X. And you can get adaptive algorithms that are unbiased in this limit that are efficient. Okay, so how does this connect back to the subspace ideas I talked about earlier? Well, what you could do is just let, at each iteration, my pk be sampled according to a distribution whose expectation is ak. Okay, so, right, this can be done. An expectation is kind of like I'm taking a step in this preconditioned Langevin direction. And notice that if I know the eigendecomposition of this pk, again, I only need to compute r coordinate directional derivatives corresponding to the UK transpose grad v instead of all of them at each iteration. And then the dk takes care of preconditioning. Okay, so this is our general framework for this subspace Langevin Monte Carlo algorithm. There are many choices you could use, right, for what distribution pk comes from, but it is important that it's random. Okay, so it could be, the block coordinate updates or random eigenblocks of a fixed preconditioner. But you can start to do more things, right? Like I said, maybe it depends on the distribution of the x's and the potential somehow. Notice that, if you have something like this, you don't actually need to compute the full Hessian. Right? If I sample UK, I really only need directional second derivatives. So you can get away with sort of, low dimensional approximations of the Hessian here. And maybe this is a way towards scalable adaptive Langevin algorithms. Okay, so in the last little bit of time, I want to kind of explain what changes in the theory when you add in the preconditioning. So, this whole time I've been talking about strong convexity and smoothness. What changes when you add preconditioners is you now want to measure your progress with respect to this sort of, or measure how well-behaved V is with respect to a new norm defined by this inverse preconditioner. So this function V is going to be relatively strongly convex and relatively smooth with respect to this new norm, right? That's defined by this for a general B, if this holds. Okay, so it's a little bit, if you haven't seen this before, may not look completely intuitive, but one sufficient condition for this to hold is that the Hessian of V at all points is lower bounded by little m times AK inverse, and at all points is upper bounded by capital M times AK inverse. Okay, so this is the notion of relative convexity and smoothness. If we're going to allow for changing preconditioners, they need to change slowly enough. This is just an assumption for our analysis. We need that these low-rank matrices are eigenblocks of some matrix AK. Right, so blocks of eigenvectors and eigenvalues. And the last assumption is now instead of paying directional smoothness with respect to the Euclidean directions. What I'm going to pay is directional smoothness with respect to my new norm, with respect to my relative norm. Okay, and just to kind of, I guess, really motivate why these relative convexity and smoothness are important, this is a simplification of what happens with mirror descent, is let's just say I'm in the Gaussian case, and this is my potential. Then if I look at V with respect to this norm, right, it's an immediate calculation to see that capital M and little m are just 1. So my conditioning in this case with respect to this norm is 1, but with respect to the Euclidean norm, it would be the maximum and minimum eigenvalues of this matrix. Right, so this sort of preconditioning can make things much, much better in practice. Okay, and so this is our result. Again, the result will now depend on this Wasserstein 2 distance with respect to this new norm. But this is maybe not as easy to interpret, so let's just focus on the case of a fixed preconditioner. Right, so if my preconditioner is fixed and I'm sampling eigenblocks of it, what I end up paying now is this familiar thing if I'm uniformly sampling my eigenblocks. And alternatively, if, again, I sample according to my smoothness with respect to my blocks, I can get back to a result that looks like this, and I think that there's a missing factor of R there. But right, the main thing that we see is, again, what we get or we gain by this is that now this method does much better than that standard Langevin Monte Carlo for 2 reasons. One, that we measure directional smoothness, and 2, that it's relative directional smoothness. And sorry, this should be an M, not a beta anymore. So, and this should be a kappa rel. Okay, so what this is meant to illustrate is you can, by using these subspace algorithms or approximations to the Langevin algorithm, you can achieve preconditioning, which allows you to work in relative convexity and smoothness. And you can gain in terms of directional smoothness constants. Okay, and I just want to show you in the last few minutes that this actually does help a lot. So this is an example of an ill-conditioned Gaussian distribution that you want to sample from. And the test function that I'm going to use to measure error is this absolute value of the sum of the entries of the vector. And I want to measure the expected value of 5x. And all of the methods have the same step size here. Yeah.
Why error could be negative here?
What, sorry?
Error could be negative here.
It's log error.
Sorry.
Yeah. This is a log scale to see it a little bit easier. When I look at the convergence of these various methods, what we see is that while the Langevin has the least bias in the limit, preconditioned Langevin, right, if I just apply Langevin with a preconditioner here that sort of is adapted to the structure of this matrix, right, here the preconditioner has 1s on the upper left block and 10s on the lower right block. You see it converges much faster initially, but then it has tapers off at higher bias. And we see that we're actually able to sort of match that with a subspace algorithm that matches sort of the block structure here. So the block size of 5 matches it a little bit, but doesn't match this 10 by 10 block exactly and the 10 by 10 block of the preconditioner exactly. But when I have things match up here and I get this sort of ideal scaling, you see that I get this exact sort of match between the subspace updates and the preconditioned updates. And what you could imagine is that this method converges very fast initially and then stabilizes at some bias. What you could do is you could take a more aggressive scheme of taking h to 0 here. Right? You could say, I shrink h, and then the bias should decrease as well. OK, so what this illustrates is that choices of preconditioners help, and the choice of subspace dimension actually does affect things as well. Now, if you, in this problem, again, go back to the point where we know that sigma inverse is a good preconditioner, so let's just use that. And you see when I do that, it no longer matters what size I take for my blocks, and things just converge very, very fast. So if your preconditioner is well adapted to your problem, you get fast convergence, maybe with higher bias. But again, what you can do is then shrink the step size to get to lower bias. OK, and maybe in a more realistic problem, right, we're not going to sample from Gaussians with the Langevin diffusion. Let's look at a Bayesian logistic regression problem. This is only 2 dimensions, but again, it's just meant to illustrate what happens. So here it's an ill-conditioned Bayesian logistic regression problem. You see my contours of the distribution are very skinny. And I'm comparing here samples from a Langevin Monte Carlo with a small step size with a subspace Langevin, where I now take the preconditioner to be this Hessian inverse. OK, so this is a preconditioner that's adapted to the contours of my distribution now. And the subspace Langevin here is taking updates only in one direction. So at each iteration, I don't need to compute the full Hessian. I only need to compute, say, one directional second derivative. And just to maybe show you, right, like when you run these things, it's, again, this is meant to illustrate that having proper adaptation is really important for these algorithms because they allow you to better explore the contours, whereas in ill-conditioned cases, Langevin can really fail. OK, so with that, I just want to wrap up. So main point is subspace Langevin allows you to move from dependence on strong convexity and smoothness to dependence on relative condition numbers as well as directional condition numbers. But unfortunately, for the current analysis, I didn't tell you how to select a good sequence of preconditioners. There are lots of choices in the literature, right? Adaptive methods in optimization are all over the place. So hopefully we can draw ideas from those and prove convergence of those. But that is maybe a subject of ongoing work. And I think that there are some really nice connections between this as well, right? There are other preconditioned Wasserstein flows that have been looked at recently, like these covariance modulated transport flows, where again you see a positive definite matrix that only depends on the measure, but doesn't depend on position, that changes the geometry of Wasserstein space. And I think that low-rank approximations of these are probably better bets to use in practice just because you don't want to be working with high-dimensional matrices in general. And so I think that there might be some nice connections between low-rank approximations or randomized approximations of things like this. All right, thank you.